Alright, so we're looking at a couple other applications of tangents and normals. I just want to do three together here, and then I'm going to give you guys the opportunity to practice on your own. One thing is I graded the tests that were already taken, and those are online, by the way. There was a correlation between the level of focus of doing the problems in class when I gave you time to work in class and the outcome on the test. Alright, those who were kind of chatting more than they were working didn't do so hot, okay? This is the kind of thing that you have to practice, alright? So make sure that when I give you time later to work on these, that you're using that time wisely, because this is the time that you can ask questions, you can work out those little issues that you might have to get things right, okay? So let's start first of all here with tangent, the tangent to a trig function at a particular point. Here we have y equals the tangent of x. So we want the equation of the tangent to y equals tangent of x at the point where x equals pi over 4. Alright, so pi over 4. So when we're finding the equation of the tangent line, anytime you're finding the equation of a line, you need a point, and you need the slope. What's the point that we're going to use here? Pi over 4, and then what would the tangent of pi over 4 equal? 1, because that's your 45, right? So sine and cosine are both root 2 over 2, so that's 1. By the way, when we get to our IB review time, we will take some time to review our unit circle a little bit, so we might be a little rusty. But anyways, we have the point here, pi over 4, 1. Now we need the slope. So how are we going to find the slope? Taking the derivative, alright? So, dy dx, this actually is one on the formula sheet, or in the formula booklet, they give you the derivatives of sine, cosine, and tangent. Does anyone remember what that is off the top of their heads?
It's positive, for sure.
It's positive, because only the cos were negative, right? Yeah. Positive secant squared x. And actually the formula booklet, they take it a little easier on you, because they even give that to you in terms of cosine. It would be 1 over cosine squared of x. Alright? By the way, this is the type of thing that would be on the no-calc part. Alright, they would expect you to know your unit circle well enough to do this. So if we have 1 over cosine squared of x, then the slope when x is pi over 4 is going to be 1 over the cosine squared of pi over 4. Well, what is the cosine of pi over 4?
Root 2 over 2.
Root 2 over 2. So I have 1 over root 2 over 2 squared. What's root 2 over 2 squared? A half, so 1 over a half would be 2. Okay? One over a half would be 2. So now I can find the equation of my line. If I use point slope form, 2 times x minus pi over 4 equals y minus 1, and then I can solve it. 2x minus pi over 2, if I distribute the 2 to the pi over 4, equals y minus 1 you could decide kind of what form you wanted this to end up in. If you wanted it in the slope-intercept form, you could have it as y equals 2x minus pi over 2 plus 1. If you wanted it in standard form, you could have it as 2x minus y equals pi over 2 minus 1. I'd bring the y over to the left and the pi over 2 to the right. Either one of these would be fine. Okay. Does anyone have any questions about what we've done here? Really just another specific application of the first application we looked at, finding the equations of tangent lines. Okay. Now these last two are a little variation on this, okay? This next one's kind of interesting. Finding where a tangent meets a curve again. Right? You might say, well, I thought a tangent line was only intersected something once. And at the point we're looking at, that is true. But because we're dealing with functions here, it is possible, and actually it's probable, that a tangent line will not only be not only intersect near that tangent, but also will intersect it somewhere else. For example, this isn't meant to model this equation here, but just so you see kind of what we're talking about, if I were finding the tangent at this point right here, right, that would look like this, okay? And obviously, at this point, it only intersects the curve once, but because the curve comes back up, we end up hitting it again down here. Alright? So one thing that we can do is look at, hey, if this is a tangent line, where will we intercept that again? Okay? So in other words, if there was this path, but we went off at this point, where could we pick it up again? If we went tangent to the path, off, where could we pick it up again? Okay? Maybe it's a windy road and we slid off the road, okay, on a tangent. Alright, so rather than fighting our way back to the road, we just decide to keep going straight until we hit the road again. Okay, that's kind of a silly illustration of what's going on here. Okay, but think about the situation. How would we go about figuring this out? What do you think?
You can find another point on the tangent line, and then you can see where.
What do we think? What two equations?
The tangent equation and the original equation.
Okay. We have this original curve. We can find the equation of the tangent line, right? So then we could just solve for when are those going to be equal? When do they intersect? Okay? Now this problem actually is a really good one that brings back to memory some things from very early in SL math in our advanced algebra studies. Let's take a look at it, okay? The first thing that we need to do is find the equation of this tangent line, all right? So we're going to run through the same process. They told us this was the point 14. Okay, and again, this is not drawn accurately with this curve at all, okay? But there's our 0.14. To find the equation of the tangent line, we already know the point. We need the slope. Okay, so again, we take the derivative, 3x squared plus 1 is the derivative of that function. What do we plug in to find our slope? 1. We plug in the x coordinate of the point we want to hit. Alright, so at x equals 1, the slope is 3 times 1 squared plus 1, so that is 4. So I know the equation of this line is 4, so obviously my drawing is off because I have it going down instead of up. Alright, but that's okay, this isn't modeling. That's not modeling this specific problem, so let me delete that. Alright, so now we can get the equation of our tangent line. We have the 0.14, it's 4 times x minus 1 equals y minus 4. So that comes out to y equals 4x. Because we have 4x minus 4, then we add the 4 from the other side, and we just get y equals 4x. Now, we said that to find where they intersect, we're going to set the equations equal to each other. Alright? So, our original equation, y equaled x cubed plus x plus 2. Our tangent line, y equals 4x. Okay? Now think with me here. I already know one of the answers. What's one of the answers? 1. Because I know these lines intersect at the 0.14, right? So I know one of my solutions is x equals 1. But let's look at how we would find the other ones. I'm going to get this equal to 0. X squared minus, or not squared, that would make it easier. X cubed minus 3x plus 2 equals 0.
But since you have a factor already, you can take out an x plus 1, and then you can do the quadratic on that.
We can take out an x minus 1. The question is, what is the quadratic left over?
Reducing synthetic division for you?
Yeah. And that's the tying it back to what you did a long time ago, and you may or may not remember, okay? So notice, since I know the answer is 1, one of the answers is 1, I can take that out as a factor of x minus 1. Then what I'll have left is a quadratic, and once we get it to a quadratic, those are easy to solve, okay? So this is where the synthetic division comes into play. Alright.
X squared minus 2.
So let's run this through since it's been a while. Okay, remember the answer, the root that we know is going to be that root we're going to use here, the 1. Okay, then we list the coefficients of all the powers of x. So we have 1x cubed. 0x squared minus 3x plus 2. And then you remember the process?
You bring the first one down.
Okay, bring it down,
And then multiply.
then multiply it up, add it down, multiply up. And it should end up being 0 because we know it actually is a root. Remember, that's how you could test, if you remember the rational root theorem. You could test to find a root by doing this and seeing if you ended up with 0. Now, here's a couple of numbers, but what does that mean?
That's the
X squared.
no, remainder and constant, you gotta go
Yeah.
backwards.
That's the remainder is 0, so that's good. We have no remainder.
Constant,
Constant,
x,
x, and x squared. Notice here, guys, you had an x cubed, and you're factoring out an x. If you factor out an x from an x cubed, you end up with a x squared. So that's why every column, the power decreases, okay? So now I know in here is an x squared plus x minus 2. And you know what that factors into?
Add to one.
X plus 2, x minus 1. Okay? So guess what? Our answers are 1, -2, and 1. Well, 1 being a double root, that actually does happen when you have a tangent. Okay? When you're finding intersection points, if you get a double root, it's actually tangent at that point. But the -2 is the one that we're really interested in here. Okay? Because that's going to be the other spot
and
where this thing intersects. Okay? So, -2, how do I find the rest of the point?
To the original, or no, you put
What?
plug it into
Plug it in for x where?
the original.
The original. We're trying to find a point on the graph, right? So plug it into the original function. Or, since it's going to be a point on the tangent line, you could plug it into this as well. Which is a little simpler. 4 times -2 is -8. Okay? So this right here is where we're going to intersect the curve again. Alright. I don't know why that's doing that. Alright. Any questions, comments, anything? Kind of a neat application, alright? Kind of a neat application. How do we meet back up with the path that we were taking if we go off on a tangent? You know? So. Alright, our last application is kind of an interesting one. And I gave you the picture from the, this is an example straight from the book. I gave you the picture from the book, but the picture is actually a little bit deceiving, okay? I want to find the equation of the tangents, plural, to y equals x squared from the external point 2, 3. Now, understand what we're talking about with an external point. If it were a point inside the parabola, okay, there actually are no tangents from that point, okay? Because to draw to the curve, it's going to have to pass straight through. It's never actually going to be tangent if it's inside, alright? However, we have this point on the outside, 2, 3. Now, the reason why I said this one's a little bit deceiving is because they draw this one here, but that's not the only tangent. If we were to continue drawing this y equals x squared up this direction, we could also have a tangent going from 2, 3 up this way. Okay? So we're going to find both. Alright? This one going up and, intersecting right there. it intersects right here. This green one intersects right here. Now, both of those points can be modeled the way they gave us this point down here as a squared. Okay? Some random number a, and then if we plug that into our function y equals x squared, we get a squared as the y coordinate. Okay? Now, the key to this is to recognize two things. First of all, we already know a point on the line. We already have our point 2, 3. So really what we need to do is identify what the slope is going to be. Okay? And the way we're going to do that is actually in two different ways. The slope, first of all, when I say slope, you're thinking what at this point?
Derivative.
Derivative, okay? So dy dx equals 2x. So at x equals a, the slope equals 2a, right? But secondly, we can also find the slope another way. Instead of by the derivative, we actually can see 2 points on this line, right? We have the point 2, 3, and we have the point a squared. So our slope we could write as a squared minus 3 over a minus 2, simply using rise over run. The reason why we have to do that is because we had two unknowns here. We didn't know what the slope was supposed to be. We didn't know what a was supposed to be. So we needed a second equation. So now we have it. And now we can set our slopes equal to each other because they're going to be the same. 2a equals a squared minus 3 over a minus 2. And now we have an equation to solve. Does everyone follow up to that point before we start solving? Now, how many different a's are we going to get? 2. That'll give us this a and this a up here. Okay? We'll get 2 a's, so we'll actually be able to find both of those points. Okay? That'll also tell us both of the slopes that we're going to use so we can get both of the lines. Alright? Yes?
And where'd you get the a squared minus 3 over a minus 2?
I did my slope formula, the y minus the y and the x minus the x, using the 2 points that I knew were on the line.
Okay.
Alright, so now we're going to multiply by a minus 2 to get it out of the denominator. We have a 2a squared minus 4a equals a squared minus 3. I want my a squared to stay positive, so I'm going to bring everything over here to the left. So it's a squared minus 4a plus 3 equals 0. How does that factor?
Minus 1.
There we go, a minus 1, a minus 3. So a is 1 or 3. Okay? So for this green line, since in our picture at least it's the one to the left, okay, I'm gonna make this green line then. It's hitting this, what's our point of contact?
A squared.
A squared, which if this one is where A is 1, it would be 1, 1, right? There's the point of contact. And remember, point of contact or point of tangency is the same thing. Okay, so there's our point of contact. What would it be for the red line? 3, 9. Okay? What's our slope for the green line, where A is 1? What's the slope of the tangent line? 2A, right? So our slope here is 2. 2 times 1. Okay? And then the slope over here, if A is 3, our slope is 6. Okay? Now again, the problem didn't ask us for the point of contact, we found that just for the fun of it. When we got our equation, we could have just used the 0.23 for both of them, or you can use the point of contact for them. It doesn't matter which you use. Alright, but since I've gotten them written here, I'll go ahead and find the equation using the point of contact. Alright, so our slope times x minus 1 equals y minus 1, and that's going to give us the equation y equals 2x minus 1. Over here, 6 times x minus 3 equals y minus 9. So that's 6x minus 18 plus the 9 is 6x minus 9 equals y. And those are our two lines, our two tangent lines. Alright. So, there's some good problem solving here. You've got to be able to put what we're doing now together with whatever we've done in the past. Whether it's using synthetic division to find extra roots, or whether it's something as simple as our slope formula. You know, you may have to use systems of equations, but where did that other equation come from? It can come from something very simple, like a slope formula or something like that. Okay? So, just be aware of that and, you know, be a good problem solver. Keep trying. If it doesn't come to you right away, try some other things. Write down all the facts. Make sure you know what all the terms involved mean. And think about those terms. Okay, how do those terms relate to what we've been studying? Is there anything else that I could tie in here that would help? Okay, so what I want you guys to do at this point, I have one copy of the book that if someone wants to use that instead of the online copy. What I want you to do though is work together, and you can pick and choose from the problems here. Alright, you don't need to just go straight through all of them, but page 389, 9 to 16, this is picking up from where your homework left off. There are some good ones in here where you're really having to do some problem solving. Challenge yourself. Use this time wisely, okay? You're welcome to work on the board. You can work at your seat, but you gotta be working on this, okay? So, alright, let's go.